Hello, class. Well, unfortunately, as you guys can tell, I'm not here today because I decided to accidentally crush a toe of mine during the weekend with a cast iron. Yay! I should be back on Tuesday. Just know that there will be some changes to the classroom. The tables are probably going to be rearranged within the coming weeks, and that also may include a seating chart. Because it seems that the two long tables have been a bit of an issue in every single period. So I'm going to try to tackle it that way. It's very simple. If you are basically sitting there doing your work, and I don't mind too much noise, but if you're sitting there getting work done, you're likely to stick together. But if you're completely off task most of the time, socializing, or popping your head out of the class, or trying to leave the class randomly, I might put you a little bit further away from the door. Just let you guys know. All right. So here's the warm up. Look at the pattern up here. What one is the next one? What goes here in this question mark? So you have A, B, C, or D. So go ahead and give it a pause, give it a shot, and try and figure that out. Welcome back. The thing is with this, if you're paying attention, we are just turning it, as you see. When we turn it again, so we're going to turn it one last time. And what does that match up with? Well, looking around, we see it matches up perfectly with B. So that's the one we would be looking at. So inductive reasoning is what we're covering today. We are going to have a preview of what a proof looks like at one point. And on days I do give you guys proofs. If I'm giving you a fair amount, we might have that roll into 2 days. But just know that is around the corner. All right. So we're going to have a look at inductive reasoning, your term, conjecture, a counterexample, and upcoming proofs. A review should be sequence. We're recently covering that. And a new vocabulary is conjecture or idea. A counterexample, something that disproves. And inductive reasoning, looking for patterns. They'll all be defined here soon. Inductive reasoning. It's a type of reasoning that reaches conclusions based on pattern of specific examples or past events. That is the definition. It's a type of reasoning that reaches a conclusion based on patterns of specific examples or past events. Example, here is we're going to use inductive reasoning to determine the next two terms. 78, 80, 82, 84, 86. You should be automatically thinking 88. Because we're adding 2 every single time. Let's just come back to that. So every single time we're adding 2, as you can see. So then when we add 2 again, we get 88. And after that, we're going to get 90. So that's what we're doing. We're just looking for patterns. That is a pattern. This is a case of a pattern. All right. So give it a go. This one should be easy. As you see, we're going to look for the next 3 terms. You should be thinking 65, 65, 65, 55, 60, 65, 65, 60, 55, 65, 60, 55. Sorry about the little tongue tie there. I was going backwards. Anyways, so you see that all we're doing is decreasing by 5. These are where the sequences are coming back. Sequences are inductive reasonings. So you more of a visual. At one point, there was a popular gaming console that had an pin option. Think of Wii bowling without looking up how many rows would be needed for one pin game, that 100 pin game. So we can start setting up the bowling game. First one, we have 1 row down here, 1 pin. Then we have 2, total 3, 2 rows. 3, 6 pins, 3. Add 4 for the 4th row. Add 5 for the 5th row. So you notice that every time we add a row, it adds that exact many. So next one, you're expecting 6. And we're going to keep on going. 7, 8, 9. Notice the number is getting a little bit bigger. So at this point, it's just going to get really big because we're at 54 plus 10. Then it's going to start increasing a little bit more. 65 with 11, 77 with the 12, 90 with the 13. But now we're at 104 with the 14. So if you're looking at that particular one, what they needed to remove 4. And what they usually did was remove the last 2 and this 2, kind of making this arrow pattern. So this is what they did for the 100-pin bowling game. At least for the Wii. I think they also did it for the Switch. All right. So conjecture. Here's what the definition of a conjecture. A conjecture is an unproven statement or rule based on inductive reasoning. So again, a conjecture is an unproven statement or rule that is based on inductive reasoning. What conjecture can be made about the dots in the nth term of this geometric pattern? So the first one, we see first term, we have 2 dots. Second term, we have 6 dots. Third term, we have 12 dots. And the fourth term, we have 20 dots. So what do you notice? Something I notice is first time we have a row of 2, then we add one more to the row, but also another column, 4 and 3. So there must be some sort of pattern there. So 1 row, 2 columns, 2 rows, 3 columns. So a general equation for n would result in the following. The columns, as you see, we're going to be looking at whatever number we have plus 1. 1 plus 1 gets us 2. 2 plus 1 gets us 3. 3 plus 1 gets us 4. 1, 2, 3, 4. 4 plus 1 gets us 5. All right? And what are we timesing it by? N. 1 times 2 is 2. And when it is 2, we have 2 times 2 plus 1 is 3 plus times 2 is 6. So we have this equation. I'm going to grab that and move it right on up. So this is our equation. All right? So it's just looking for these and finding out the patterns. Another way we can write it is n squared plus n, distributing the n. So that's the 2 ways we can write that equation. So the second conjecture, these are the triangular numbers. This is another pattern that does come around in mathematics. We have 1, 3, 6, 9. So what can you formulate for a conjecture? We have 1 here, then we added a 2, then we have another kind of triangle forming and another triangle forming. So start at 1, going to 3, going to 6. Okay, so if you're looking back here, notice that we have 6 here and 6 here. But that comes a little later. So it's very similar to this one as we see here. So the equation for this one would be n times n plus 1. But think about it for a second. We had 2 here, 1 up here, 6, 3, 12, 6, 20, 10. So how can we modify this equation to make it so it works? 1/2. Divide everything by 2. So apply that to our equation. N times n plus 1 divided by 2. All right? Very straightforward. So give this one a go. Look for a pattern. So discuss amongst yourselves and figure out what the pattern could be. Notice that we go from 1 to 4 to 9 to 16. And it should be hinting right here. All right. Welcome back. If you're thinking it's just n squared, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, you would be on the right track. All right. So a counterexample shows that the conjecture is false. Because a counterexample is an example that shows the statement is false. That it's not always true. That's what a counterexample is. A counterexample is an example that shows the statement or conjecture is false. How many do we need? Just 1. So is the following statement true? A polygon with with diagonals has 2 fewer diagonals compared to the sides. What I'm saying is, if you look at here, we have 0 diagonals for the triangle. We're looking for things that go across. So we have 3 sides, 0 diagonals. It's true. For the square, we can do 2 diagonals for the 4 sides. So it must be true, right? Let's have a look here. Okay. So if we're looking at this, we're going to go and play around with this for a second. Notice we already seen this. In fact, let's just make it a nice, more of a greenish blue color and reduce it a little bit. So if you've seen this, we already seen that. And then we just went to the 4. Number sides 4, number diagonals 2. So as soon as we find something that makes our statement, which is a polygon with diagonals has 2 fewer diagonals compared to sides. As soon as we find the sides and diagonals almost even, we're good. So let's look at 5. 5 sides. The pentagon has 5 sides and 5 diagonals. And as you look, as soon as we get to 6, the number of diagonals passes the number of sides. So you see that that statement is only true for the triangle and quad. As soon as you get beyond that, it's no longer true. In fact, you can even keep on going to the point where you reach the maximum amount of sides that this particular GeoGebra problem thing has, which I did find made by this guy up here. But if you go up to a 50-sided, it's a pentagon with 50 sides and over 1,000 diagonals. So it's almost a circle, but it's not really a circle. As you can see, it does have a slight edge right here. But overall, it does look pretty interesting if you move right on in. That looks like a spirograph. Anyways, so let's just go ahead and get back to the thing. So you can see that this is false. So try to disprove. A prime number, a number that's only divisible by 1 in itself. That's just a reminder. This is just kind of like basically you'll be using little definitions like this to help with proofs. So conjecture. Consider 3, 13, and 23. 3 is a prime, 13 is a prime, 23s are all prime. Thus, I'm saying every number that ends in 3 is prime. Go ahead and find one number that ends in 3 that doesn't work. So give it a thought, think about it, and you could be saying the very next number, 33. 33 ends in 3, but 33 is 3 times 11. That's no longer prime. There's also numbers like 63. So there's plenty of them. 93. All right. So give this one a go as well. It's a bit of a challenge. The composite number is a number that's not prime, kind of like 33. Divisor is not one in itself. Here's an example. 4, which is 1, 2, and 4. The sum, addition of two composite numbers, is always going to result as a composite. Is there any counter example? So what I'm asking you to do is to add two composite numbers and try to find one that results in a prime. Alright, so give it a thought and try to answer it. And give it a pause. Welcome back. So if you're thinking about it, a number you could be thinking about is, well, 6 is composite, or 4 is composite, right? What about 9? 9 is also composite. But 9 plus 4 gets us 13, a prime number. That is just one example. Alright? So accompanying proofs, this is a good reason to take notes. This will be coming your guys' way later on this week, I believe it's or next week. It's either this week or next week you guys are going to have proofs, but I do believe it's next week that you'll have your intro to a proof handout. So just bear that in mind. Alright? And if anything, this is the only type of proof I'm probably going to try to give you. It's a 2-column proof, maybe a paragraph proof. I'm going to try to keep it more on the down low. But I will be giving you guys a very handy handout that you might want to keep for your guys' notes, because it gives you all sorts of reasons that you could be using or saying, I can use this because I see this. Okay? You'll see it when we get to it. But this is what a 2-column proof looks like. We are given a statement. We can say this, and this is the reason we say it. All right? So let's put it to work. So if A, B, C, and D are points on a line in that given order, and AB is equal to CD. Normally, if they give you something like this, you want to use it as given statements. We're trying to prove, I'm going to move this over here at this point, AC, starting at A, ending at C, is equal to BD. All right? We are given A, B, and C, D. So A starting at A, going to B, is equal to C going to D. So let's go ahead and put that right on in. So, and also says they're collinear. So that is given right here. A, B, C, and D are points on a line that give no order. They are collinear. That's given. AB is equal to CD. That's also given. So when you're given something like this, if you can, if it's not necessary in a book, you might want to write it out accurately, write on the diagram. So AB is equal to CD. So you want to put a dash here and a dash there, showing that they are congruent. Now, if we can have basically BC be equal to itself, we can set something up pretty easily. BC is equal to BC because it's reflexive. Think of it this way. What the reflexive property means is 5 is equal to 5. So whatever the length BC is equal to, it's going to equal to itself. All right? So we can use a reflexive property using that. And that reflexive property is also included on that one page that you guys will be getting. So just for your guys' a heads up for you guys. Okay. So notice we can create this line, A starting at A, ending at C. But it's going to be equal to the line starting at B, ending to D. And that's exactly what we're trying to say, but we can't just say it right now. Even though it's there, we have to spell it out for them. You have to be very, very specific. So we can say BC plus AB is equal to BC plus CD. And we can say this is the addition property of equality. Basically what I'm saying is, since these two are equal and these two are equal, the green ones are equal, the orange ones are equal. Since the green ones are equal, and we can add those to the orange ones, which are also equal, to make the same exact distance. If, for instance, AB was 2, BC was 3, 2 plus 3 is equal to 3 plus 2. That's what we're saying. So we can then say, using angle or segment addition postulate, which we did cover in the past, A plus B, A to B plus B to C creates the line A to C. That's what it says right here. And B to C plus C to D creates the entire segment B to D. That's what we're saying here. So segment addition postulate. Notice that we are almost there. The last thing we need to do is use substitution. So if we pull down our line, we can substitute the BD for the BC plus CD. Then we can substitute right here that BC plus AB, this first part, has AC. So when we substitute that in, we get AC is equal to BD. That is how we're going to be working on the proofs. And when we first start this, I am going to give you guys like 2 days to work on through the one handout. And if I give you guys proofs in the future, that might also be the case. Okay? So I should be back on Tuesday, just as a reminder that as soon as I'm able to, with the crushed dough slightly, I will be rearranging the rooms just slightly and the table slightly, getting some of the smaller tables, things like that, and trying to break up the more groups that just want to sit there and socialize. All right, have a nice one.